All right, so in this video, we're going to look at finding the area between two polar curves. Now, it should be noted that these problems can be quite different from problem to problem. So it's important to very carefully read the relationship and where the area is for the curves that you're trying to solve for. In some problems, they will say inside one curve and outside the other curve. And sometimes they will say outside this curve and inside the other curve. And sometimes they will say shared in between the, shared area between the two curves inside both curves. So you want to be very careful when you're reading these problems because changing one word can change the region that you're trying to solve for. Now, in this particular example, we're looking at this circle of radius 2 and this cardioid, and we're trying to find the area inside both the circle and the cardioid. And so one of the things that we're going to need to know is where we flip over from cardioid to circle as our potential boundary. And so we're going to start by setting these two equations equal to each other and solving for theta. So in this case, if we set these equal, we have 2 on both sides of the equation, so those cancel out. And then we solve for cosine theta, and cosine will be 0 at negative pi over 2 and pi over 2. So these are our boundary conditions right here. Now, it's very tempting to just simply have one area integral and to simply try to find the area which is bounded here by this circle in between these two limits. But the kind of problem that we're doing here is actually going to require us to be a little bit more careful because we also have to deal with area that is bounded specifically by the cardioid, but which is still inside the circle. And so let's look at this graph a little bit more carefully and make sure that we are setting up our area correctly. So when we plot the pi over 2 angles, we end up with one angle right here. And then let's change colors. We end up with the other angle down here. Now, if we were to integrate from, let's say, negative pi over 2 to pi over 2, then what we're doing is we're going around from here to here. And so the outer boundary of the region is just the circle. But that's not actually the whole problem because there is some additional region that we have to deal with when we are in here and in here. And so we can't actually neglect these sections. In these sections, we're inside the circle, but we're bounded by the cardioid. And so we're also going to have to consider both of these sections when we set up our integral. Now, we may consider the possibility of using multiple integrals to do this. And in this case, we are going to need multiple integrals with multiple boundary conditions. But we can also use symmetry to make our life a little bit easier. So let us consider just above the x-axis here. If we calculate this area up here above the x-axis, bounded by the circle, and then also this section right here, bounded by just the cardioid, but still inside the circle, then, and we double it, then that will get us the entire area, and we won't need to set up all of these individual sections. It will allow our an algebra to be a little bit less terrible. So our area is going to be 2 times, and then our area for inside here, remember our formula is 1/2 the integral of r squared, so that'll be 2 squared d theta. And our limits here are going to be starting at 0 and going up here to pi over 2. And then that's the 1/2, the one section. And then we will have a separate one. And here we're going to pick up at pi over 2. And if we're only going down to the x-axis, then we're going to go to pi. And the boundary for this section is going to be the cardioid squared. So this is messing up our spacing a little bit. Put it down here. There we go. All right. And then I need to close my bracket. There we go. Now the 2 then is going to be very useful. It's going to cancel out these 1/2 for us, but then we will have a bit of algebra that we'll have to do. So let us actually do that algebra. So we're going to end up with, let's see, the 2 and the halves are going to cancel. So this integral is going to be relatively straightforward because this is just 4 d theta. And then this one, we're going to have to multiply out a bit. Let's see. 2 times 2 is 4. And then 2 times 2 cosine is 4 cosine, and times 2 again. It's going to be 8 cosine. And then 4 cosine squared. And we're going to need to substitute for the cosine squared. So before we integrate, let's do that algebra. So this cosine squared is going to get replaced with 1/2. 1 plus cosine 2 theta. And the 4 and the half are going to simplify. So that's going to become a 2. And then we distribute the 2 through the 1 plus cosine 2 theta, and we get 2 plus 2 cosine 2 theta. And we can combine the 2 and the 4 to get 6. And so now we can integrate all of this. For theta, from 0 to I over 2. And then 6 theta plus 8 sine theta. And then our 2 gets canceled out when we integrate. And so that becomes just sine of 2 theta. And then all of this gets evaluated between pi over 2 and pi. And 4 times pi over 2 is going to be 2 pi. And then we're going to have 6 pi minus pi over 2. And when you plug pi into sine, you get 0, but then you're going to get minus 8 times sine of pi over 2 is 1. And then when you plug in pi into sine of 2 theta, you're going to get 0. And when you plug in sine of pi over 2 times 2 into that, you're also going to get 0. And so we're going to end up with, let's see, this will be pi over 2 times 6 will be 3 pi. So that'll be 5 pi minus 8 as our final solution. Now, again, it's important to keep in mind when you're doing these examples, when you're doing these problems, you have to plot out the angles on your graph and make sure that you're including the entire region that you're looking for, because you may have to set up different integrals. In another video, I may do some examples where we do, let's say, this outside region, because here it's going to be bounded on the outside by the cardioid and on the inside by the circle. And so that is a whole other problem in and of itself.